Hello, everyone, and welcome back to another episode of your favorite algorithm channel. Today we're going to be doing LeetCode 21, Merge Two Sorted Lists. First of all, I just want to say we just broke double digits on our subscribers for this channel. I reached 10 today, which is phenomenal. And I just want to congratulate all of you guys for following my YouTube channel. Thank you very much, and hopefully more subscribers to come. But without further ado, let's introduce today's problem. So today's problem is merge two sorted lists. So we are merging two sorted linked lists, and we need to return it as a new list. It's kind of misleading wording there. I guess it is kind of a new list. But the new list should be made of splicing together the nodes of the first two lists. So we're not creating a new linked list. Like, we're not creating brand new nodes and transferring the values. We're actually physically rearranging the pointers so that these two lists are in the correct order, right? So we're going to get two linked lists if we look at the example here. So 1 to 2 to 4, and then this other one 1 to 3 to 4, and we should get the output of a linked list that's 1 1 2 3 4 4, right? So I find sometimes it's kind of tricky in problems like these. If you haven't done a lot of linked list problems, what you want to return is you're returning the first node. You need to return the first node for this problem. So the output would be you need to maintain a pointer to the front of your list. So we're going to maintain a pointer to the front of the list. We're going to weave these two lists together, rearranging the pointers, not creating brand new nodes and changing the values. And it shouldn't be too difficult. So one thing I should point out, if you don't do a lot of LeetCode problems, you do get the linked list for free. If you look up here, you'll see the definition for singly linked list, and there's this function here. This is you can use this. It's list node. It is a list node, right? So this is kind of built in. You get that for free. It's only like 3 lines of code. I'm sure you could write your own function for this, but just know that you can just use what they have. And if you want to modify it a little bit, just override it. Just write your own, but just make sure that you use list node, because otherwise you'll probably fail the problem no matter what you do. So just make sure you're using either this or override it with your own definition of a linked list. So as always, I encourage you to solve the problem on your own. I think you guys can tackle this one today. And if you get stuck or you just want to see how I did it, then check out the video after you solve the problem. So if you are ready to get started, come with me to the whiteboard. On the screen here, I have 2 linked lists. So at the top here, I have a linked list that's comprised of 3 nodes. So it's 1 to 3 to 5. And then on the bottom, I have another linked list that is 4 nodes. That is 2, 4, 6, and 8. And what we want to do is we want to merge these 2 lists together. What we don't want to do is create a brand new linked list, right? We don't want to just create new nodes transferring the values. We actually want to physically move the pointers themselves. So we want to rearrange these nodes so that they're in sorted order. And the fact that both of these lists are already in sorted order means that we can easily incrementally step through both of these lists, taking the lesser value at each iteration and just rearrange the pointers. So over here on the other side of the screen, we have a head node that we're just going to attach the lesser of the 2 nodes to, and then walk our way through the list and attaching all of our nodes to this head here. And then we have a pointer to this head. And then once we're done, we can just return ohead.next, original head.next. And then we have this other pointer here, which is pointing to head. And as we walk through our 2 lists, we also want to keep track of what is the last node that we merged, right? So we're going to be keeping track of 3 pointers here. We're going to be keeping track of the pointer to the front of our first list that we're going to merge. We're going to be keeping track of a pointer here that's going to be pointing at the head of the second list that we're going to be merging. And then we're also going to be keeping track of the last node that we merged. So let's walk through how this function works and get a better idea of how it's going to work. So if we look at our 2 front pointers, that's pointing, so one of the pointers is pointing to 1, the other is pointing to 2, right? So we can evaluate that 1 is less than 2. So we will move 1 to be attached to head, keeping our pointer intact to 3, and we'll increment our pointer to 3 and increment our head pointer to 1 because this is the last node that we have merged. And then we'll evaluate, okay, is 3 less than 2? No, it's not, so we'll take 2. Maintaining the pointer to pointing to 4, and then we'll move our pointers. So we'll move the second head pointer to be the next node in that list, and we'll move our head pointer on our merged list to the last node that we have merged. So now we'll evaluate 3 and 4. We'll see that 3 is less than 4. We'll maintain a pointer to 5, and then we'll increment our pointer to be the next node in both of our lists. And now we'll compare 4 and 5. We'll see that 4 is less than 5. Maintaining the pointer to 6, we will then increment to the next node in both the merged list and the list that we're merging. And now we'll evaluate 5 and 6. We'll see that 5 is less than 6. So we'll merge 5 into our list, maintain the pointer to null, and then we'll increment our pointers. And now at this stage, one of our pointers has terminated to the end of its list, right? So we're at null. So because both of our lists are sorted, we know that we can just change our pointer to be the head of whatever list still has remaining nodes in it, right? So that would just be pointing to 6, right? And now we're done. So not an overly complicated function, but this will come in handy when we do a function later on or algorithm later on called merge case sorted list. This is the subproblem to that bigger problem, and it will become handy to just be able to whip up a function like this very easily. So it's a good one to know. It's a good one to review. So what is the time complexity of this problem? Well, the time complexity of this problem is big O of n plus m. And why is it m plus m? Well, because you can imagine a scenario in which we would have to interweave every single node in both lists, and they were the same length. So we would have to touch every single node to actually successfully merge that linked list together. So now that we have a pretty good idea of how this function works, let's see what it looks like in code. So let's start by creating a head pointer. So our head pointer is just going to be, and we want to make sure that's a let, not a const, because we're going to want to reassign it, just a new list node. And we'll just assign its value to null. And then we also want to maintain a connection to the front of the list. So we'll create a pointer for that, and we'll just point it at head. And then while L1 and L2, so while we haven't terminated on either of our lists, while they're still pointing at nodes, we want to keep traversing through both lists. So so we want to assign head dot next to be equal to if L1 dot val is less than L2 dot val. Then we want head dot next to be equal to L1. Otherwise, we want it to be equal to L2. And if if L1 dot val is less than L2 dot val, then we also want to increment L1 to be equal to L1 dot next. And we want to do the same thing for L2. And then the last thing we want to do is just make sure that we're updating our head pointer. So we want to say that head is now equal to head dot next. And then finally, after we have gone through and terminated on one of our lists, we just want to make sure that if there are any remaining nodes, that we're attaching those to the end of our merged list. So we'll just say that head dot next is equal to, so if L1, then we'll say it's equal to L1. Otherwise, we'll say it's equal to L2. And then we'll just return ohead.next at the end. So just to recap, we created a head pointer to attach our nodes to, and then we just created a pointer to point back at the front of our list so we can return it at the end. And then while both of our lists are still haven't terminated to null, then we want to reassign the head, the next pointer for our head to be the lesser of those two values. And then depending on whichever one we ended up assigning to be merged, we want to increment that to be the next value. And then we also want to do the same thing. We want to then move our head pointer as well. So then here, after we have gone through both lists, if there are any remaining nodes, we want to attach those to the end of our merged list. And then we just return the list at the end. Okay, so the complexity, or the optimal complexity for this problem is also, again, fairly straightforward. The runtime is big O of n plus m. So in order to merge all these lists, we have to look at or in the worst case, we have to look at all the nodes, right? There's no other way to do that. So this is the optimal strategy for solving this problem. I would like to encourage everyone out there, if you like this video, to check out some of my other videos. All these are a part of my playlist, the LeetCode Top 100. So if you want to do the LeetCode Top 100 with me, I'm going to keep putting out these videos. I'm going to try to do them every day, but I probably won't do them every day. But I'm going to try to make my way all the way through the top 100. I believe we're 11 questions in right now. So if you're interested in coding along with me through this 100 algorithm challenge, please subscribe to my channel and keep checking out my videos, and be sure to go back and look at any ones if you want to catch up with me. I hope you enjoyed the video, and I hope to see you in the next one.